Welcome. In today's lecture, we're going to take a look at three different light phenomena: internal reflection, dispersion, and the polarization of light. So first, let's consider an extreme case of the bending of light that goes by the name total internal reflection. Total internal reflection. Now, this is a special case that occurs only with a certain set of index or indices of refraction such that N1 is greater than N2. So remember, N, the index of refraction, refers to the speed of light in that material. So if N1 is the greater of the materials, then that material slows light more. So we're talking about light going from slow to fast medium. This only happens in this particular arrangement. It doesn't work going fast to slow, just slow to fast. So some examples of this would be light traveling from water to air, if the light begins underwater. Light traveling from glass to air, or even, say, glass to water. As long as it's going to a smaller index of refraction, we can end up with this phenomenon. So I'll draw a picture to go with this. Let's say this is our boundary between the two materials. Over here on the left, we'll have our slow medium. So this is going to be N1, the first index of refraction. Then we go into a faster medium or material, the index of refraction N2. And we have a ray of light striking that interface at a certain angle of incidence. And so remember, our angles are always measured from the normal line. So I'm going to draw that imaginary perpendicular line. So the angle that this strikes, theta 1, angle of incidence, is right here. And so if we go back to our wheels and mud metaphor, this is a car that's driving through the mud. It's going to hit the pavement. The wheel on the right is going to grip the pavement before the wheel on the left. And it's going to cause it to pick up speed, and it's going to bend this way. It's going to bend away from the normal line. And so here's my refracted ray of light. And here's my angle theta 2, my angle of refraction. So I know Snell's law describes this. N1 sine theta 1 equals N2 sine theta 2 to represent this relationship, which, if I'm interested in knowing what the angle of refraction is, theta 2, I can get sine theta 2 by itself. So sine theta 2 is going to be equal to N1 over N2 sine theta 1. So just algebraically rearrange that in terms of the two indexes of refraction. And since we'll see, and we look at this picture right here, we see that because we're going from slow to fast medium, it's going to bend away from the normal. We see that sine theta 2 is going to be bigger than sine theta 1. We can also justify that because we've said that N1 has to be bigger than N2, so this number has to be bigger than 1. So sine theta 2 has to be the bigger of the two variables, or theta 2 is always larger than theta 1. In other words, there's more bending when we enter into the new medium than when we begin in the first medium. Okay. So there must be some case, some extreme case, some value of angle of incidence theta 1, something less than 90 degrees. It has to be less than 90 degrees because this angle right here looks like it's about 30 degrees. If it hit at 90 degrees, well, it wouldn't really hit at all. It would just be moving parallel to the surface. So the incident angle always has to be less than 90 degrees in order to hit the boundary. But there must be some angle theta 1 such that theta 2 is equal to 90 degrees. In other words, a case where this angle becomes so large that it actually, instead of passing into the new medium, it bends so much that it just moves right along the interface. And this is a really interesting case. In this particular case, when we reach it, the ray of light never passes the boundary. It always stays on the same side. Well, like most things in physics, sometimes a picture can be a really helpful way of understanding a principle. So I'm going to draw a picture that will consider four different cases. So here I have my boundary, my slow medium and my fast medium, and I have four different rays of light that are all striking that same interface and then picking up speed. Now remember that the angle of incidence is always measured from a normal line. So as I go from left to right, I can see that my angle of incidence is increasing. Now I see that the light is going to pass into the new medium, in one case, in the first case, in a straight line, speeding up but not changing direction. In the second case, we get some refraction since it strikes at an angle, and of course it bends away from the normal, just like we've been talking about, where theta 2 is bigger than theta 1. But if I allow it to strike at a big enough angle, it will bend so much that theta 2 will become 90 degrees. So when theta 2, this is the interesting case, when theta 2 becomes 90 degrees, notice how the light just moves right along the surface and it never passes into the fast medium. If this is glass, it never passes into the air. Which, of course, then raises the question, what would happen in the last case where can it bend more than 90 degrees? Well, it doesn't really bend more than 90 degrees, at which case, if theta 1 is even bigger, it just bounces off the interface and stays in the same medium so that it obeys the law of reflection. So if it hits at a 60-degree angle, it bounces off at a 60-degree angle. So these two cases right here are called total internal reflection. And any amount of any angle that it strikes bigger than this angle right here, this is the transition point, so we're going to call this theta critical. This is my critical angle. And when it hits at the critical angle or bigger, it stays in the material. So if a ray strikes at an angle greater than or equal to the critical angle, it stays in the medium. So how do we know what the critical angle is for a set of materials? Well, let's apply Snell's law. We're going to have it strike at an angle. Let's say that my angle of incidence is the critical angle. We want to figure out what that is. And then that's equal to N2, and at the critical angle, the angle of refraction is 90 degrees. Now, the sine of 90 degrees is just 1. So we can come up with a relationship now to figure out what the critical angle is. The sine of the critical angle is simply going to be N2 divided by N1. So this ratio of index of refraction can be used to determine the critical angle. So please add that to your equation card and we can figure out when total internal reflection occurs. So looking at this example right here, we can see we're interested in figuring out the critical angle for a glass-air surface. So let's say the light begins in glass and goes to air. So we find our critical angle. Sine theta of the critical, or sine of the critical theta, is equal to N2 over N1. So N2 is the slower medium, so in this case, or excuse me, the faster medium, it's going to be air, and then the original medium is my slower medium, N1 is going to start off in glass. So I've got air, which has an index of refraction of approximately 1. Glass, I'm told, is 1.52. So I've got 1 over 1.52. We'll take the inverse sine of that, and we'll find our critical angle, in this case 41 degrees. So light that begins in glass, if it strikes anything less than a 41-degree angle, it will pass into air, but if it strikes more than a 41-degree angle, it will stay in the glass. Now there are all kinds of fascinating examples and applications of total internal reflection. One of them is something called the Poro prism. It's a 45-45-90 prism, so it's basically a piece of plastic or glass so we got a 90-degree angle here, and these two angles are each 45. And it has an index of refraction such that it basically acts like a mirror. And so we've got light striking the first surface, going from air to glass. It slows down a little bit, but keeps going in a straight line. And it strikes here, and so here's my normal line right here, and it strikes at an angle greater than the angle of critical. So I've got my critical angle here, something greater than the critical angle, and it stays inside the material. It bounces, and then it does the same thing right here. It's going to bounce again, and it's going to pass back out the other side. So it's just bounced around inside that material without actually leaving. And mirrors, turns out, don't even do this very well. If you have light strike a regular mirror, there's going to be some absorption of that light energy, and they don't perfectly reflect the light. The light's a little dimmer after striking a mirror, a shiny surface, but in this case, bouncing around in the material and passing out becomes a lot more efficient. So you find these in certain types of binoculars where you want to gather a lot of light from these big lenses that are out here. The light comes in, and it can be bounced around inside a set of Poro prisms and then sent to your eye as a way of kind of moving where that light beam is. So we wanted to draw this ourselves. So here comes the incident ray, it hits the medium, it slows down, keeps going in a straight line because it strikes it straight on. And if we look at the geometry of this triangle, this angle here is 45 degrees. So we just need to have a critical angle that's 45 degrees or smaller, in which case it can't pass out into the new material. We get reflection. Strikes the next boundary at 45 degrees as well. Another reflection. And it passes back out like this. Another really good example of where this might happen naturally, or I suppose the diamond, cut diamond isn't naturally, but when a diamond is cut a certain way, is the diamond, being a very slow medium for light, can trap light and allow it to bounce around on the different faces, just like you would see in a poro prism. So as we see here in this case, we can see a diamond. White light enters the diamond. We get some reflection at the surface. We get some bouncing around, just like in the poro prism, and the light leaves. And what ends up happening is light ends up actually bouncing around many different times before it actually leaves. And based on the actual cut of the diamond, the shape of the diamond, the angle has to, so you kind of see this cone representing the critical angle. As long as we are within or outside of that critical angle, then the light will stay in the material. You just want to make sure the diamond isn't cut too shallowly, because if it hits less than the critical angle, the light can leave. And the more bouncing around, the more sparkly, and it ends up colorful the diamond will appear. Another very cool example of total internal reflection is fiber optics, like this cable over here where we got light traveling through the curved cable. You can keep light trapped inside a medium as long as it doesn't curve too much. If it curves too much, then it might strike at the wrong angle, something less than the critical angle, and allow it to escape. So let's draw a picture that might show this relationship. So let's suppose that this is a piece of clear plastic, and we're going to shine some light into this. Like a laser beam. The light enters like this, and it strikes. Here's the angle of incidence. Notice it's a really big angle, and if this is, glass and then air, or plastic and then air, it could be totally internally reflected instead of passing out. Stay in the material. And notice as long as it keeps hitting at these really big angles, it stays in the medium and bounces around, traveling in one direction until we get to here. And then if it curves too much, it might actually refract out. So here we've got too much curve. Resulting in the escaping of our light. And fiber optics have many advantages for sending information. You can pulse the light on and off to send the bits of binary language, of digital electronics, and some of the advantages are listed down here below.